So, hello everyone. I'm Greg Cohen from the Western Sydney University, from the newly formed International Centre for Neuromorphic Systems, which is about a month and a half old now. We were going to be the Australian Centre for Neuromorphic Engineering, but ACNE is not a great acronym. So we went with ICNS instead. So I'm going to talk today about something a little different from everyone else. I'm actually going to talk about an application of neuromorphic engineering, and one where it's really exciting, where we can prove that a neuromorphic approach actually has advantage over the conventional way of doing things. And it's a little different. It's a little out there, well, very out there, because we're actually talking about space imaging. So putting these cameras in telescopes and looking up. And, well, I guess before I start, I'm going to just go through a few points that I want you to keep in mind while I'm talking. I'm going to come back to these as I go along, but it's just nice to put them out in front here. The first one is the importance of active sensing. And that's actually in the title of this talk. And the idea is that this talk's all about using neuromorphic cameras, so the ATIS, the Davis, any of these DVS sensors. And one of the interesting things about them is that they're really fast. And as a result, you can image while you move the sensor. And that lets you do things you can't normally do with a camera. And if you know the motion of your sensor, you can use that to extract far more information out of the scene. You can also then incorporate motion into how you sense and how you detect things. Simply put, you can say, given what I'm seeing, what do I look at next? And that kind of ties into the next point, which is this idea of expectation and prediction. So if you have a little network, and its purpose is to try and predict what it's going to see next, you don't really care about what that network's predicting. What you care about is the difference between what you're predicting and what you're actually seeing. That tells you if you're seeing what you expect to see. Because what you really care about is when you see something you don't expect to see, or just as importantly, you don't see something you expected to see. That's novelty. That means you have to do something. If you're seeing exactly what you expect, your model of the world is consistent, and you usually don't have to do anything. That's kind of what the camera itself is doing. But if you sort of persist this thinking right through the whole processing chain, then you get the benefits right through and through. What I'll also show you is how you can use this high temporal resolution, this active sensing paradigm, to essentially increase your spatial resolution. So these cameras don't have fantastic spatial resolution compared to conventional cameras, but they're fast. And that's kind of what we do. We move our fovea around, we build this high resolution image of the world. The next point we've touched on a few times before in talks at this workshop, which is the importance of synchronization. For example, the stereo matching problem becomes a coincidence detector. With the work I'm going to show you now, that becomes even more important, because we're now talking about putting telescopes in parts of Australia. And if we can synchronize those, we're not synchronizing frames anymore. We're synchronizing changes at each pixel. And when it comes to fast-moving objects in space, that's what you need to solve the ranging problem. The next point is probably kind of more apparent to this audience than most, but essentially everything I'm talking about today is biologically inspired. I'm not claiming any plausibility. My goal is to actually solve an application. I want to do space imaging or space situational awareness better. So my goal is to be biologically inspired and solve the problem as best I can. And last and not least, as we always talked about, everything I'm talking about today is primarily from telescopes on the ground, so we're not power sensitive here. But if you put these things in space, you're now on a power, size, and weight constrained platform. So the idea of having low power, low bandwidth sensors is extremely important. And not just in the sensing, in the computing as well. The moment you take the data from these cameras and make frames out of it, you lose a lot of that benefit. If you can process the data in the same format that you're getting it, without ever moving away from the events, then you get these benefits through and through. And I guess this is really the point that I'd like you to try to take from this talk, which is that I think if you're doing a computer vision problem and you're using a conventional camera, unless you're taking photos, you're using the wrong tool. You're taking everything. If you want to solve a task, just take what you need. For tracking satellites, which is what I'm going to talk about today, we don't want full images of the sky. There's a lot of just empty pixels there. All I really want is x, y, and velocity for the objects I see. And if that's all I can extract to the sensor, that's all I have to transmit down to Earth from a satellite, for example, and that saves power and bandwidth. So I think the first thing is I'm going to talk briefly about the field of space situational awareness. That's the defense side of it. On the civilian side, we call it space traffic management. But it's the same thing. In the broad sense, it's really just trying to figure out what's going on, well, basically where all the objects in Earth orbit are. Everything we put up there, which includes active satellites and a whole bunch of space junk and bits of rockets. Essentially, we've got to the point now where we've been launching things into space for 60 years now. It's getting really crowded up there, and we do a terrible job of figuring out where these things are. So the risk of collision between objects is growing. It makes launching satellites and launching manned missions even more difficult and dangerous. And also, if you just think how dependent we are on satellites for almost everything we do, from communications, for weather, for navigation, for example, this is critical infrastructure that touches every part of our lives. And truth be told, it can take one catastrophic event to destroy a big chunk of that. So this is kind of the setup at the moment. It's a bit misleading because all the objects are the same size. But ultimately, there's a lot of space junk up there. So I'm going to talk a little bit about the different types of orbital regimes that we're interested in. The first and probably the most common is low Earth orbit, or LEO. That's about 400 to 1,000 kilometers above Earth. That's where you'll find the International Space Station, the Hubble telescope, and all the CubeSats. So whenever you hear about someone putting up a CubeSat, it's going to low Earth orbit. When you hear about people putting up thousands of constellations, or constellation of thousands of satellites, it's going in low Earth orbit as well. So this is getting really congested. And this is where we really need to do a better job of tracking things. Currently, we can only track down to a few centimeters at best, so 10 to 30 centimeter objects. And there's about 30,000 of those actively tracked, and who knows how many more that we're not tracking. So moving up from low Earth orbit, you get to what we call middle Earth orbit, or medium Earth orbit. And that's essentially, you can't really see it so well on this projector, but there's not that many objects out there, and that's because this is kind of the intermediate area. You're not protected by as much as the atmosphere as you do in low Earth orbit, but you also have these long transfer times. So in low Earth orbit, your cycle around the Earth is about 90 minutes. Up here, it can be up to 12 hours. That's where all your GPS satellites are. But you're not going to worry about radiation hardening, and these get bigger and bigger satellites. It's also more expensive to put things up there. But perhaps the most critical and one of the busiest parts of space is the geobelt, the geosynchronous orbit. So that's that ring you see out there of satellites. That's a very specific distance above Earth at which the orbit of the satellite matches the orbit of the rotation of the Earth perfectly. Put a satellite up in that orbit, it stays exactly above a point on the ground as the Earth turns. That's where we put all our communication satellites. It's highly contested. It's really getting full. And when we put the first satellites up there, we had no plan for what to do with them in 20 years when they started failing and dying. So we have no plan to get rid of them. So this is the part of space that everyone's interested in looking into. So how do neuromorphic cameras fit into that? Well, it turns out that event-based cameras are fantastic for space imaging. We can do things with these cameras you simply can't do with a normal camera. So you guys are probably familiar at this point with how these cameras work, but really the take-home message with this from me is you can't use conventional computer vision algorithms on this data. You need to come up with ways of doing things from the ground up to work with the data in the format that it comes out of the camera. What we're going to make use of here is the fact that pixels are independent and asynchronous. So the fact is, if you point one of these cameras at the sky, not much is changing, so you don't get data from all the back pixels that are just looking at empty space. If something like a satellite enters the field of view, we only get events from that satellite and really quickly, so we can start tracking it really within microseconds of seeing it, actually. We also have this high dynamic range, and that lets us do something that no one else can do. With an optical telescope, I can track satellites during the day. And if you're running an observatory, and you can only work at night, and suddenly someone comes along and says, hey, I can work during the day, it doubles your efficiency, straight off the bat. So these are some of my telescopes. This is how we started. This was about 2 years ago with the Defense Science and Technology Department in Australia. We had two setups that we initially worked with, a 2-telescope setup you see on the left there, and a 3-telescope setup on the right. I like to show these pictures because if you look at the 2 telescopes on the left, you'll see what we've done is we've taken 2 telescopes and both sides of them so they look at the same part of the sky. We put them on a robotic mount so we can actively track and point accurately at space. The top one has a ground truth sensor. That's an astronomy camera. That's a $60,000 Finger Lakes Instrument Astronomy CCD. It's a spectacular piece of kit. It's actively cooled. It's a highly refined piece of engineering. On that bottom telescope is the event-based camera I did my PhD with. It's shoddy, and I can attest to that because I put it together myself, and you can see the screws hanging out of it. So the point really is that this is baseline performance with these cameras. These aren't built specifically for space imaging. So we can only make them better. And that's really the take-home message from that one. From the middle pane, you'll see a picture down at the 2 telescopes. And what you'll see there is that the top telescope has this very sophisticated aperture made of a piece of cardboard. The reason is that when you look at some of the objects in the sky, even the bright objects at night, they're so bright that you need to actually use that little aperture just so we can see anything. For the bottom camera and the event-based camera, because of this high dynamic range we have, we don't need to do anything. We can focus the camera and forget about it. So even the daytime operation, same set of optics. Then we moved on to this 3-telescope setup, and I'll show you some results from that one as well. Now we've got 3 telescopes all ball-sighted and 2 event-based cameras on each side of the ground truth sensor. One is an HS camera, one's a Davis camera. And that was important because now we can say what we're seeing is not specific to one camera or one telescope. Recently, we've even upgraded from this, and we built the setup over here. This is a container with a telescope, so the roof slides off. Scissor lift lifts the telescope up, and we have an observatory. We can do this because we can move the sensor, and therefore we can tolerate motion in the sensor. So if you go to any other astronomer and you ask them about building an observatory, they will want to sink 4 meters of concrete into the ground, right, and build an observatory on it. I can put it into a shipping container, move it anywhere, plug it in, and essentially track satellites. This is a capability, and then we moved it to the Avalon Air Show last month, which was quite spectacular, although they wouldn't let us point anything at the plane, so we had to put the lens caps on. So I apologize for this. We like our bad puns in Western Sydney. So we named this thing the Astrosite. Yeah. Well, I finally found an audience who finds the joke funny. All right, so let me show you what data looks like from one of these cameras. This is the first recording we ever took. This is Mars from an event-based camera. You can see it's bouncing up and down a bit. That's because we were really excited and jumping up and down next to the telescope. But you might also see that there's a sort of circular rotation to the data. That's atmospheric scintillation, and I'll talk about that in a little bit. So this is actually a big deal for us. When we had the camera focused, no one had ever done this before. We actually could see things. It's really exciting. So the same night, we just had the camera pointed at an empty piece of sky. And this was the aha moment because we saw this come through the field of view over here. No idea what that was at the time. We had all these arguments about it being planes, but we were in controlled airspace. We thought it might be high-velocity moths, but it couldn't be that. Turns out it's low-Earth orbit satellites. And we can detect them. Now, to give you an idea of what it looks like on a conventional camera, this is the results from the astronomy camera. It produces an image every 4 seconds, so it has a 2-second exposure time, 2-second download time. You can see the satellite in the bottom left-hand side there moving through the field of view. It's a long elongated blob because you're integrating and everything's moving. That's how they do it conventionally. I'll show you what the data looks like from an event-based camera when you track the same object. This is a Russian rocket body that's tumbling, by the way. This is what you get. On the left is a frame. On the right is a graph of the events with time as the vertical axis. And you can see you're getting far more information out of this, and you're getting continuously and in real time. Not only can we detect the object, now in this case we're moving the telescope to keep it in the field of view, and there's a star streaking through. Not only can we detect it and see it there, but that stream of events from the object contains a whole bunch of information. We can actually see, for example, if a satellite is tumbling, it'll glint occasionally, and you'll see these gaps in the data rate. We may be able to go even further than that and tell more about the satellites from it, but this is a really whole different way of doing space imaging that's enabled by the neuromorphic hardware that we're using. The way of approaching imaging. It's a different paradigm. So you can also do this by keeping the telescope still and pointing, or just moving with the stars so you don't see them, and watching the objects move through the field of view. So these are satellites passing through as we're static. So the idea is that, if everything in space is always moving. Now, the trick, of course, is that this works nicely for low Earth orbit satellites. But remember, I said that geosynchronous satellites are relatively stationary relative to us on the ground. So if you want to see them, well, they're not moving. So the answer is active sensing. You move. So this is what a geosynchronous satellite looks like on a normal telescope. If you take a picture, you have to integrate over some time. All the stars become streaks because they're moving. But that dot in the middle there is the geosynchronous satellite. To see that, what we do is we move the telescope actively. We essentially pan the telescope across the sky. You can't see very much on the left-hand side, but just by doing a little bit of post-processing, you can see the geosynchronous satellite moving down the field of view there, which is actually us moving the telescope. And that's a particularly apt way of saying it because this is done during the day. We can see these objects in the day. And this is actually a really big deal because there's really no way for you to monitor these during the day in half the world at any given time. And it's probably one of the most important national security priorities is to figure out what's going on in the geobelt. So the next video is probably my favorite in the whole slideshow. It's low Earth orbit satellites from 2 different event-based cameras simultaneously. That 3 telescope setup I showed you there. Left is an ATIS camera, right is a Davis camera. They have overlapping field of views, but the field of view of the one camera is smaller than the other. That constant object there is Canopus. It's a star that we just use for reference sake. And what you're seeing moving through the field of view are low Earth orbit satellites. And at the bottom, what we're doing with the hardware and the processing we do is extracting the trajectories and plotting them. Right, so we're plotting the trajectories of the objects moving through the field of view. That's the data you really care about. If we built this as a system, we'd want to take as much of the processing, putting it at the sensor as possible, and just output these tracks rather than all the data that you see at the top there. The really great thing about this is done at 4 o'clock in the afternoon in Adelaide. It's a very civilized time to do astronomy. This is what happens when you make an engineer do astronomy. They get lazy and they want to figure out how to do it during the day. But this is something that no one else can do. You can't point a normal camera at the sky and take images this way. So I'll go back quickly to adaptive optics and atmospheric scintillation. This is Jupiter and one of its moons from an event-based camera. And you'll see that cyclic pattern I was talking about over there. That's the atmosphere moving between us and the object we're seeing. And that's a big problem for astronomers. It makes everything blurry. But it turns out that with event-based cameras, we're sampling this really fast. And there are ways to compensate with adaptive mirrors. And we could build a pretty good wavefront sensor with these cameras as it stands, but we might be so fast that we could algorithmically remove the scintillation and get back to the original image by modeling it. It also turns out that scintillation is actually quite useful. So I'll show you a simulation we put together just to show how that's useful in a second. And what you'll see there is you'll see some white blobs, which are showing where the stars are. And when we remove them, you'll see the events that would generate on the sensor. On the left, you'll see a plot with no scintillation. On the right, this is actually what it looks like. This is atmospheric wobble. This is the moon through a normal camera. And that wobble is just the atmosphere moving. In the simulation here, you'll see those white dots. When they disappear without scintillation, you just see the outline of them. With scintillation, it spreads that information over the whole area of the star, so you actually get to see it a little bit better. When you add noise to the equation, you'll see how important that becomes. With the scintillation and with the noise, you can still see the objects. Without the scintillation, it's almost impossible to see it. So scintillation helps us, and with these cameras, what we can do is we can use the scintillation to help us see objects, and then still perhaps even walk back that atmospheric distortion and get to the original data behind. So we can have our cake and eat it. All right, so the next thing I'm going to show you is a bit of star mapping. This is a picture from a conventional camera of the sky. It's just where the stars are. We want to figure out if we can generate this from an event-based camera. Turns out it's pretty easy. Take the camera, point it at a piece of the sky, so you're just staring, and let the stars rotate through with the rotation of the Earth. Top left is the raw data you're seeing from the camera. Bottom left is the sort of inference surface that basically says, I know how fast the stars are rotating through the field of view. So if I see a star here and I see it over there again, I'm pretty sure that it's a star now, and I can add it to this growing map of the sky above me. And that's an inference map. So the longer we observe, the more and more certain we get. And we can build up these really long star maps of the sky. The two important things to note is this is an entirely passive process. We can do other things. We can still catch fast-moving objects while we're doing that. But there's no reason why we have to wait for the Earth to turn. We can actively move. So we can swing backwards and forwards across the geobelt and build up a high-resolution image of all these satellites there. And we get sub-pixel resolution in the direction of motion, while still catching fast-moving satellites. So that gets really exciting. So we also just showed that if you overlay the two, it actually matches up, and you can actually do the astrometry. You can figure out where you're looking in the sky just based on the stars you're seeing. But what I showed you there is just a tiny segment of a huge, long, full-night recording of the sky. So you can really do this in a different way. We're now going to the point that we can relax a whole bunch more parameters in this, where we can actually handle what we call non-uniform jerk. So you can basically swing the telescope around, and it can still track and figure out where in the sky it's looking, without using the intrinsic pointing model in the telescope. So the next thing I'm going to show you is one of my favorite recordings. This is the clouds passing in front of the moon with an event-based camera. This is an old recording on an 80s camera, so you've got the change events on the left, and the moon the reconstructed grayscale on the right-hand side there. And what you notice is the clouds pass in front of us, they're actually helping us. They're inducing change. And that's interesting for two reasons. Firstly, we can do astronomy when it's lightly cloudy, which is kind of cool in itself. But there's two velocities here, and it turns out it becomes really interesting when you try to say, well, can I separate those two based on velocity? Can I separate the clouds and the object behind it, because I know they're moving at different speeds? Turns out you can, so we did. Top left is the raw data. On the right-hand side is the map of those clouds passing in front of the sensor that we know are moving faster, and in the bottom left is a map of the moon forming behind it. So this turns out to be really computationally easy when you just work with the data. So this in itself is an interesting problem. I'm not sure where the relevance is in space, but we came up with this looking at space. So we started with a defined application, came up with an idea, and then said, well, can we apply it somewhere else? So we thought, what about terrestrially? So we put together a little experiment. In our lab, we got this very sophisticated stick wall, put the camera on a translation platform so we can move it backwards and forwards. And the idea was to say, well, when the camera's looking straight on, it can see through all the gaps in that stick wall. Right? And then when we move it, we know how we're moving. So we know where the gaps are moving as well. And the pixels are seeing through that see the world as if the sticks aren't there. And we also know there's parallax. So the objects closer to the camera are going to move at a different velocity to the objects further away. So can we recreate what's on the other side? We used to call this seeing through bushes, but the university got upset with that and said, no, change it to occlusion invariant sensing. But either way, the scene we're trying to image is this scene from our lab over there. There's my colleague standing there and some objects on the table. Let's have a traffic cone in the lab. I don't know where that came from. But watch what happens when you do it with the normal camera. So the normal camera moving across, you can see the sticks okay. But you have exposure issues. With the event-based camera, top left is the raw data from the camera. Top right is trying to image the sticks, which doesn't work so well. But the bottom two images are the near field and the far field, generated with two different velocities. In the far field on the right-hand side there, you can see my colleague standing in the structure of the room appearing. On the left-hand side, or the right-hand side for you guys, you'll start even seeing the objects on the table. That's one pass. If we went backwards and forwards enough times, we probably could read the label on the wine bottle. So this is just an idea of how you can take a defined application for these cameras, build a system specifically to solve that. And once you have an application, you know exactly what data you're getting at. You understand how to do essentially you know what constraints you need on your system at every point. It becomes much easier to build an end-to-end system when you know the task you're trying to do. And that's not necessarily as specific as you might think it is, because in that process of solving the one task, you might constrain the problem, see an opportunity, a solution, and be able to take that and apply it to other fields. in this case terrestrially. So this is a really exciting bit of research. In fact, at the moment now, that AstroSite container is now in the deserts of South Australia tracking satellites for us. And the idea is to roll out a network of these around Australia. And I think at that point I might just leave it, but I will leave you with some dramatic footage of the last year of us collecting data in the deserts of South Australia. So thank you so much.
Thank you, Greg, for the animated presentation. Are there any questions?
Couple of questions. So the first one is, I guess that this, I mean, you didn't give any details about this separation of clouds and the underlying thing. It's just a low-pass, high-pass filter, or what's the?
Well, it's almost an inference problem. You say, I have two velocities. Which one explains the events I'm seeing better? And you will lose some events. But essentially, you just use local patches and structure. And you say, well, which movement explains those better? So it's an expectation problem.
OK. Second one is that you mentioned that you may have like a satellite tracking all satellites and so on. Whenever you go outside the atmosphere or in low Earth orbit, you get lots of radiation and so on. I mean, in my experience, it's very hard to convince anyone to let you put a CPU from even like, the early 90s in space. So how, I mean, how would those cameras deal with radiation, and how are you going to convince anyone to put one of those in space?
Okay. Well, I've got two. So firstly, I have two space missions coming up. One launches is supposed to launch in June, and a potential ISS mission for 2021. So I've convinced people to let me put them in space. And the answer to your second part is I think there's an opportunity for neuromorphic in space for a reason that is actually, it's about graceful degradation. If you built it, like take one of these cameras, if you lose a single pixel on these cameras, just that pixel dies. The rest of the sense is largely unaffected because they're all independent. If you had an actual network of neurons with analog neurons and you lost one neuron in your network, it doesn't brick the whole device. You just have a bit of graceful degradation in the performance. So I think there's more opportunities in space. It's actually a way to sell neuromorphic equipment. And there's interest in that, saying, well, can you build sensors and systems that degrade gracefully as they get hit by radiation, which will happen in space, especially if you have a small satellite that isn't shielded.
You said, I mean, you showed some 3D graphs when you were tracking the low Earth orbit satellites. What were is that like a 3D graph of space? Oh, space? Like what were the axes?
So it's X, Y, it's the focal plane with time as the vertical axis. I should have said that, sorry. Okay. So it's time, so you're essentially looking down time. And
just another question. I assume that the telescopes track like in the visual spectrum. Could you use this like in a radio telescope or an infrared sensor? So radio is a bit more tricky, but infrared absolutely. And truth be told, in the infrared spectrum, all you care about is changes. You don't care about producing nice pictures of the infrared spectrum most of the time. So I think there are really exciting applications when you go to other spectra as well.
How small is the debris that you can detect?
Sorry? Oh, one sec.
Can you detect debris, like from satellites, old satellites, or how small is the object that you can detect? So it becomes, at some point, it becomes an optics problem and an atmospheric problem. We've seen 1U CubeSats, which is about 100 by 100. But technically speaking, if you had the right set of optics and a precise enough mount, and you could do corrections for the atmosphere, you could see smaller than that. To give you an idea, radar, which is the gold standard for producing the sort of space tracking data, they can usually see down to half a meter for the standard system to about maybe 100 centimeters for radar cross-section. So, we're competitive with that without trying. So the trick really is at some point you just need enough light and you need it to get to you in a collimated way. Okay. Thanks, Greg.
Thank you so much.